So I am Rocq at Madras. I work on programming languages, model application and systems. I am also co-maintainer of the OCaml programming language, which I'll talk to you about a bit more today. And I also run a company called Tarides, and I'm the CTO there. So Tarides is an open source company, and the goal of the company is to build systems, and we want these systems to be functional, and we think functional programming languages are a wonderful fit for this. So we use OCaml a lot. The company also works on maintaining lots of the platform tools around the OCaml ecosystem, like build systems and so on. We also are a major contributor to the OCaml compiler itself, which I'll talk about a little bit more. So, how many of you know what this terminal is? Okay. Oh, a lot of people. Okay, wonderful. Okay, so I learned program C in this IDE. It's called Turbo C++, right? IDE. But I was very young. I assumed that the language that I was programming in is like perfect and final, right? Just like the mountains and rivers that we see around us are. But then you grow up and realize that, okay, mountains and oceans and seas also change over millions of years. Programming languages also evolve, right? But it's just very hard to see how they evolve. So the talk is more of sort of a way for me to give some more information on how the evolution happens, right? What are the forces that is driving this evolution? So that's basically the point of the talk. I have worked on a few languages. I worked on OCaml for the past decade. So I would base my observations specifically on OCaml. How many of you have heard of OCaml? Oh, a lot of pieces. Okay. I will tell you about why OCaml is so good. So it is a functional paired programming language, but it has multi-paradigm support as well. So it has a wonderful object-oriented system. It has imperative features. You can just write programs that look like Fortran and OCaml. Right? One of the reasons why it was designed was to help engineers write Fortran code in a high-level language. It has what is known as a static write system. So, and it has type inference as well. So you write your programs, types are automatically inferred. There are lots of advanced features which are liked by industrial users. I won't go into all of them, but recently it has obtained multicore support and support for epic handlers, which I will touch upon later during the talk. So OCaml produces fast native code, so it can compile to x86, ARM, RISC-V, etc. It can also compile very nicely to JavaScript and WebAssembly. So one of the OCaml is a pioneer here. So WebAssembly 3.0 spec was considered complete a few days ago, and that builds in garbage collection as a feature in WebAssembly. And OCaml is one of the languages that took advantage of the garbage collection feature as the first language. Bunch of platform tools, editors, build systems, all of them are there, and the company works on making sure that these tools work. There is an ecosystem of very well written but small package ecosystem. You will find it's not as large as Python, but it's small and we like it. There are a bunch of notable industrial users, some of you whom you might recognize from Surai. So one of the big reasons why industrial users like OCaml is what is known as its high dynamic range. OCaml is great for writing lots of things, including scripts to large-scale scalable systems. A lot of the people here may build research prototypes in OCaml, but a lot of people also build production infrastructure in OCaml. So here are some examples. So OCaml is a language that is tailor-made for writing compilers. Hack is a language from Facebook, Meta, right? So Facebook app is written in this language called Hack, which is a statically typed language on top of PHP. And the compiler for Hack is written in OCaml. The first version of the Rust programming language was also written in OCaml. And the WebAssembly reference interpreter also happens to be written in OCaml. So if you want to contribute to WebAssembly, you have to write some OCaml. OCaml also compiles to JavaScript. So there is this very big SEO tools company called the Ahrefs. So they write all of their front ends in OCaml and compile to JavaScript, and that's what they deploy, right? So it's a great language for writing web front ends as well. If you use Docker on Mac or Windows, the reason why Docker for Mac and Windows app works is because OCaml. So it's the reason why you can run Linux containers on non-Linux hosts. So there's a very nice papers that will be in ICFP, International Conference on Functional Programming, on the experience report around this. I encourage you to have a look. We also launched OCaml into space earlier this year. So Parsimony is a spin-out of Claridis, where it's building this operating system for space. And we launched a little CubeSat with some OCaml code running on it in order to maintain, in order to manage containers in space. And it was launched on a space-age rocket. So some OCaml code that I wrote is running in space now. OCaml is also great for writing correct code, right? So it's heavily used in finance. One of the big companies that use OCaml is Jane Street. So they have 60 million plus lines of code in OCaml. They write all of their systems using OCaml, right? From large-scale trading systems to the UIs that the traders use, to even writing FPGAs, right? So they write OCaml code that runs domain-specific programs on FPGAs. So they do deep network packet inspection for the packets coming in from the network, and all of that is also written in OCaml. Just an illustration that you can do a lot of things with OCaml, but you would be surprised to hear that OCaml is 29 years old. I'm assuming that it is older than many of you in the audience here, right? Just to drive a point home, this movie was still running in the theaters widely, right? I was corrected on Twitter. Somebody said, look, this movie is still running, so it's not a surprise, right? But yeah, it's OCaml has been around for a while, and this was the best-selling phone, right, when OCaml was released. But we are still relevant, right? We are doing interesting things even now. So how is this possible, right? So OCaml 1.0 was released in 1996, and even that time, lot of the features that industrial users like is already present in the language, like the path native backend, low latency garbage collector, and the module system. But really the history goes much longer back. So the ML in OCaml comes from meta language, Robert Milner's meta language for writing proofs in LCF theorem prover, right? And even at that point, we had this wonderful type system and type inference done. So we are basically inheriting all of that really hard work. And this was inherited by Guy Cousineau and their group, who implemented a new intermediate representation called CAM. Stands for Categorical Abstract Machine. That's what the CAM in OCaml stands for. And O was later added, that was the object system. So that's how OCaml came to be. But OCaml is still evolving. So 2012 saw OCaml 4.0 get released with GADDs, and 2022 saw OCaml 5.0 with Multicore parallelism and epic handlers. But if you sort of look at this, there is 50 plus years of steady evolution of ideas, right? And there is 30 plus years of code that is out there, right? And the question is, how do you thrive, not just survive, after 30 plus years? So one of the secret sauces that I think OCaml has is that it's very simple and stable language. So OCaml won the Sikplan Programming Languages Software Award in 2023, and Xavier Leva, who was the creator of OCaml, gave a nice talk about why OCaml succeeded. He mentioned a lot of reasons. One of the reasons he mentioned is that the language has a very simple cost model. So it is easy to just look at the code and say how much time and space you use, right? And the compiler produces efficient code that almost looks like the source code that you've written. It doesn't do aggressive optimizations. But the nice aspect is that if you want to optimize something, you make a small change in the code, you would see a similar change in the generated code. So this is a very nice aspect for the industrial users who are trying to build code that they understand. The other thing that is very nice with OCaml is you can take code from 20 years ago, and you can, it is very likely that if you take the latest compiler and compile the code will compile and run. Okay. I often invite my friends from the JavaScript ecosystem and hey, have a look at this wonderful language. You should play around with this. First thing they will do is we'll go to a package manager repository and see that most packages are not updated for 6 months. And they will say, look, the ecosystem is dead, right? Because in JavaScript, you have to keep updating things all the time now. in OCaml, the truth is that these packages are good enough. They've sort of reached a plateau where they are good enough. They will continue to remain good enough. You don't have to do anything to make these packages continue to work. So, but of course, I want to acknowledge that there is a trade-off between simplicity and stability and innovation and growth in the language ecosystem. And OCaml is fairly on the simplicity and stability side. So, if you use OCaml, you may consider that compared to other languages as a conservative language, and that's why construction, right? We like to be conservative in this space. So, a bit more on how the language development is organized. So, there are 27 maintainers today in OCaml. They come from various parts of the world: France, UK, Japan, India, and USA, across industry and academia. But the point to note here is that these are all volunteers. Not, I would think that not even one of them is paid to work on the compiler itself. So they're all working on something which may be related to the compiler development, and they volunteer their time to maintain the compiler, right? Like I do. My job allows me to work on whatever I want. I choose to pick OCaml to work on it. And the other point I want to make is that they are not the people who are designing how the language should evolve, right? They're basically the custodians of the compiler. They sort of decide what features get into the language, but not the ones who are deciding what features should get in. So who decides that? In the rest of the talk, I would like to convince you that you can contribute to the language. So there are various models of language evolution. I sort of tried to box them into a few groups. So OCaml and Python are what are known as user-driven. So as a user of the language, you can be like, look, I want this feature. And then you can propose this feature. You can implement this feature, send a PR to the language. And if it is good enough, you will just accept it. Right? This is quite different from committee-driven development of C and C++, JavaScript. There are other languages which are committee-driven as well, where there is a standards body which sort of says, here is how the committee should be. These are the people who are on the committee. They decide what the language should do and how it should evolve. Right? And there is this intermediate model which is WebAssembly, where it's open on paper. Anyone can go and participate in WebAssembly community groups. We just have to send an email and you can go participate in the discussions. But at the end of the day, WebAssembly is implemented by major browser vendors. So these 4 companies, literally 3 now, so they can sort of decide. You have to have their support for a feature to get in. And if they are not convinced, your feature will not get in, right? So that's the sort of behavior there. And the other point that I want to make is that there is no separate language and compiler in OCaml. So, IISO website, you can pay 25,000 rupees. You can download this document which describes what C language is, and the compilers implement this language. In OCaml, there is no separate language, right? Which whatever language the compiler accepts at a release is the language, right? You can sort of view this as the bar is lower for the change to the language. If you have a good idea, we can just include it in the compiler, and when we release the next version of the language, that's your feature in the language. So how is the process organized? It's an open process. All the communication, all the development happens on GitHub. So all the PRs are public. There is no private repo for maintaining code and having discussions. This often comes up in the community. Hey, the maintainers have this separate channel which we don't know of, where they're making decisions. There is no channel, right? There is a mailing list. No mail appears on the list. When a mail appears, it would be like a blue moon, right? So nobody sort of looks at the mailing list at all. Everything's open. You can go read the PRs, issues, RFCs on GitHub. The evolution itself sort of operates in this multi-speed model, where if you have a small fix or an improvement, you can make a feature request or open a PR, discuss and get that merged. So one thing that we do as maintainers is every PR needs a maintainer's approval before merging, right? That's the only, but we don't have to, we are sort of vouching, putting our mark on it. We don't have to be the person who sort of has closely reviewed it. We're sort of stamping our approval on that. But when you have large features, it gets complicated. I'll talk about one large feature that I worked on. So this may need bespoke ways to handle this. So it may need publishing papers or extensive performance evaluation, mechanized semantics, and whatnot. But the point I wanted to make is often small features, presumably small features, take a lot of time, much more time than expected. So we'll see one example of that. So OCaml does not have the equivalent of C++ vectors where you can add an element and the vector grows, right? So it only has arrays which are fixed size. And a student observed that, okay, this feature is not there. Let me add a feature. So the process is open. So they added a PR saying, look, here is a feature that I implemented. So there was a lot of support for this feature. So we want this feature in the language. But the implementation itself was, there was a lot of room for improvement. So the maintainers decided, okay, we'll have to discuss this later. So we'll close this PR for now. And then it took a long time. So 2022, and another expert in OCaml, who is also not a maintainer, came in. They worked a lot on cleaning up the API. So they developed a clean API. They put in a lot of effort. So the code was much larger now. But we discussed this a lot, 92 threads on this PR discussion, 92 comments on this thread. But there were concerns around multicore safety and performance. So we discussed this for a couple of months, and we said, okay, we need to separate this out, the API question from the implementation question. So what we decided was we'll open a separate PR just to discuss the API with a naive implementation so that the API can go in. So it went in again after 10 months of discussion, right? You can see that the conversation thread there has 342 comments here. It's keep on growing, right? But once this PR, the API PR was merged, it was easy to get that optimized implementation in. So that was merged May 2024. If you look at the summary of this, this feature was proposed in 2019 and merged in 2024. Initially, it was 200 lines of code, ended up with 2,500 lines of code eventually, right? 500 plus comments in various PRs. You might wonder whether all of this effort is required, right? And as OCaml maintainers, we believe that yes, it is, because we are. If you write code today using this dynamic arrays feature, we want it to work for the next couple of decades, right? We are not thinking about short time scales. We are thinking about code that will survive for 10, 20, 30 years, right? So we believe that this effort is necessary. And the other point is that it is much harder to undo changes after they have been made, right? So once you release a feature, people depend on it. You can't undo the changes very easily. So we are very careful about letting features in. The larger change that I would like to talk about is Multicore OCaml, which adds native support for concurrency and parallelism to OCaml. There are two separate features called effect handlers for concurrency and domains for parallelism. I'll spend a little bit of time on effect handlers later. So I led this project, so I had a chance to closely observe how this evolved. So I would like to share some lessons from that. So let's start with the challenges, right? So when you take a sequential language and make it multicore, in a garbage collected world, you need a multicore garbage collector. You need a multicore runtime system, right? This is like taking a car and replacing the engine with a new one, right? And you need to somehow make the language itself thread safe. So languages like C, C++, and even Go, when you have a data race, you don't have any semantics. Your programs can do lots of fun things. I mean, crashing is good, right? Leaking passwords is bad. They can do that, right? But OCaml is a safe language. So when your program compiles, we want the programs not to crash, not to leak your passwords, not to do open up to a huge wave of security issues, right? So we needed to come up with semantics for the language itself to have this notion of what is safe and unsafe in a multicore setting. And the biggest thing is, I'm under no illusion that just because we have this multicore feature, everyone will start writing multicore from the day it is released. 99% of the code will still remain sequential, right?
and we need to cater for those people as well. In a way, if you have a large 60 million line code base, and I said, look, you can have this multicore feature, but you have to change all of your code, that's not going to work. So, and I also want the performance of the sequential programs to remain the same on the parallel runtime. So we had a very strong goal towards maintaining feature and performance backwards compatibility. So one way we were able to do this is by building credibility by publishing key results and performing continuous rigorous evaluation. I'll tell you a lot about that later. So we started out in 2014. Our idea was to take the upstream compiler, fork it into Multicore OCaml, continue to develop it, but also downstream changes from the upstream compiler. And after a few years, we'll be at a stage where we are happy with how it evolved. So we will slowly upstream changes back to the mainstream compiler. So one of the ways by which we built confidence for this very large feature is publishing papers. So OCaml comes from this lab called Infer in France, which is an academic research lab for computer science research, right? They value academic, or OCaml's roots is also a lot in academia. We value academic research a lot. So publishing papers brings in a lot of credibility. And the way it brings in credibility is that it's not just reviewed by the maintainers, it is reviewed by the wider community of experts who know how these things work. We published a bunch of very nice papers. I will not go into depth into each of these, but for developing the compiler, this was important for us, right? Publishing results and getting them accepted was a way to unlock the door to get the feature into the compiler. I will dive a little bit deeper into one of these features which I worked on. It's called effect handlers for the concurrency story. I'll spend a little bit of time on this. So I want to define concurrent programming as in a very, very broad sense. It's a place where computations may be suspended and resumed later, right? Many languages provide concurrent programming mechanisms as primitives. So you might be familiar with a lot of these. I am not, but the observation here is that there are lots of these mechanisms which are very different. But you will also observe that there are languages which have more than one of these in, right? JavaScript has async await, generators, promises, callbacks, and so on. And it's not impossible to sort of have your end application use many of these together. So the semantics of how these interact is unclear, right? And these are not like formalized in any, these are hard to formalize generally. Okay, so we said, look, we want concurrent programming features in Multicore OCaml. How do we go about it? Which one of these different features do we pick? But we decided we are not going to build a zoo of primitives for OCaml. We are not going to add all of them. But we want the expressivity, right? Expressivity is a very loaded term. I'll try to dig into what expressivity I mean is. Really what we want is that we want the smallest primitive that can express many of the concurrent programming patterns. There are lots and lots of patterns. We don't want all of these to be implemented. We want many of those to be possible, right? That's our goal. And we ended up with this feature called effect handlers. Effect handlers are a mechanism for programming with user-defined effects. So they come from category theory, which I don't understand anything of, but they offer a very practical way to build modular and composable basis of all non-local control flow mechanisms. What does this practically mean? These mechanisms that we sort of saw in the previous slide, where there was a huge list, you would be able to implement all of them as libraries on top of this one primitive, right? And now if you are able to do that, the advantage is that in order to reason about their interaction, you just think about them as, okay, this feature is implemented as a library on top of this core feature. So I can understand the implementation interactions by their translation down to this core feature, right? So that's the promise, right? And from an operational standpoint, effect handlers are first-class restartable exceptions. So I assume many of you have programmed with exceptions. If you have the ability to sort of go back to the point of raising an exception after the exception was thrown, but also have this feature as a first class feature, which means you don't have to immediately do it. You can do it at a later point in time, right? So this is, keep this idea in mind. It will become a little bit clear. But for those who've studied continuations, all we are doing is structured programming with delimited continuations, right? You don't need to understand what delimited continuations are. I'll walk you through with a couple of examples. But the real power is that they enable lots and lots of nice programming models. So you can implement probabilistic programming, reactive UIs, resumable parsers using this one feature. In fact, a feature called React hooks. How many of you program in React here? Okay. Are you aware of React hooks? Yes. So that is directly inspired from this feature, right, in OCaml. I don't understand React hooks, but it sort of has this flavor that it is sort of seen in lots of places, right? So some OCaml code. It's okay if you can't read OCaml. I'll walk you through this. So what we are doing here is declaring a new effect called E, which when performed returns you a string value, right? Don't think about any other syntax. It's like an exception declaration, but we are declaring an effect. We have a notion of a computation which is run within this try with block. It's your try catch block in other languages. There is a notion of a handler which is like your exception handler, but it's a special one. We'll come back to that as well. With an exception, you can raise it. With an effect, you can perform it. And performing an effect suspends the current computation. And what it does is it operates after that like exception handler. So it sort of unwinds your stack, tries to find the closest matching handler, right, where the exception is handled. Here the effect is handled. So this E here is the effect that you are raising, and that is handled here. But in addition to handling this effect, you get this wonderful thing called K, which is called as a delimited continuation. Essentially, think about that as the rest of the program between the point where you perform the effect and this handler. So it sort of suspended your execution between those two places, right? Now you have a handle over this function, which you can resume using this continue primitive. So you can go back to where you left off. Now you carry this additional information that it's a string, right? So we declared initially it takes a string. Now I can resume that with a string. Okay, this is all a lot of syntax. Let's look at how it actually works in practice. So I'll walk you through the same example, but what I'll do here is on the left hand side I have the code. I'll show where my program counter is. On the right hand side, I'll show how the runtime system is actually implemented that enables effect handlers to work, right? So I have the stack here for the main function. My stack pointer is at the bottom. My stacks grow down. So when you enter the effect handler, the first thing that you do is to allocate a little piece of stack somewhere else called a fiber, and you establish a parent pointer from the current fiber to the existing one. And this fiber is just a piece of stack with the handle attached to it. There is nothing else happening, right? This fiber, this piece of stack starts out very small. It starts with 128 words, right? It's not like an 8 megabyte stack that you allocate. And you start executing, I print 0, and then now I'm just before performing this effect E. So recall that performing an effect suspends the computation. So how are we going to do that? We've done the work already, right? We've sort of split the stacks already. So all we do first is we allocate an object for this continuation and we make it point to this fiber. And then we do the usual thing that exception handlers do. Look through your dynamic context to find the matching handler. My matching handler happens to be in the main stack, right? Over here, right? So my control switch is there. But now I already have the pointer to my suspended computation over here. And what you do is you start running the effect handler. So now you print 1. Now where are we? We've suspended, and now we are just before continue. Continue is where we can resume our suspended computation. If you sort of look at this, we need to go back to where we were, right? So I have a pointer to my stack. I can attach this, I should attach this now. But the first thing that we do is we zero out this continuation. We sort of erase the pointer from the continuation to the stack because our continuations are one shot. So if two people resume the same thing, then bad things can happen. Both will end up using the same stack. So we are going to zero it out at that point. And then we restore the stack pointer, parent pointer and the stack pointer to the right place. But now what happens is we additionally carry this value 2 over here, right? This is the return value of perform. So we print 2 here, right? And now our computation is back. It executes the rest of the function. So it prints 3. 3 is printed, but something interesting happens, right? Oh, what is happening here? So the mental model that you should have for delimited continuations is like, they are like functions. You resume a delimited continuation, it returns to the position where you resumed at. So we resumed from continue. I called a function, I call that suspended function from continue. So at the point where I call it, the function returns. So we execute the rest of the computation, which is print 4, and we are done. And the point to notice here is that when this computation was done, we can immediately free this piece of stack. Just like how we when we return from a function, that space is freed, right? So we can do that as well. So I painfully walk through how the runtime system works, but this is in fact how the implementation also works, right? You can build fun things with it. So the primary reason why we added this was for adding lightweight concurrency to the language. So I'm going to show you in about 20 lines of code how we implement a full-fledged scheduler in OCaml, right? So what we do is we start with the fx that you want to declare. I want 2 functions called fork and yield. Fork takes a function, right? It's a unit arrow. Unit is like a callback that I'm going to run concurrently, right? And this unit just says that when you call fork, you don't get anything back. Yield just says I'm going to yield control, and you don't get anything back when you yield. It just comes back. So the main work happens in the run function, where you take your concurrent program and call main on it. I assume that there is just a queue of continuations here. I have not shown the code. It's a OCaml queue that just maintains a queue of continuations. The real magic happens here, right? When you call a spawn function on some particular computation f, the computation, what can a thread do, right? A thread can essentially run to completion, which is this case. When you run to completion, you just call the run next, which eventually call continue on the continuation that is already in the scheduler queue, right? You are done, you want to run the next person in the queue. But the computation can also do 2 other things, right? It can try to fork a new thread, or it can try to yield control. So those are just fx here, yield and fork. The magic thing is we have the continuation here, right? The way to think about the continuation here is it's the handle to your current thread. So when I have the handle to my current thread, I can enqueue the current thread into the queue, and I call run next in the case of yield, right? If it is a fork, I handle the current continuation, enqueue the current continuation, which means it is suspended, and I recursively call fork a spawn on this f that I want to fork. So it has its own fiber, and it runs in its own fiber. So a little piece of thing, but in 20 lines of code, you can sort of write concurrent schedulers. And you can wrap this perform and fork and yield functions, right? So you can write a little program like this, so that the user can write nice looking programs, right? So they can write a program that looks like, oh, my main function forks off 2 threads, tries to print 2 values with an yield in between. And when you run this program, you get the interleaved outputs from 2 threads, right? We've implemented concurrency, lightweight concurrency from scratch using these primitives. So that's what has happened. And the point is, the user code itself need not be aware of any of the use of effect handlers here. It's like you could have implemented this with pthreads also, right? The difference is sort of hidden underneath all of this, and that's the beauty of sort of building on top of this. There's no leaky abstraction like async await and function star for the people who programmed in JavaScript. There is all of this things that you have to do, right? All of that is gone. You don't have to pay any cost there. Languages like Haskell and Go also give you this ability, but there the lightweight threads are implemented as primitives, right? So they are part of the runtime system. You can't change that. So here we used a queue in the previous slide. I have to go through this. we used a queue here. We could have just switched the queue to a stack and you would get a LIFO scheduler, right? And LIFO is useful for certain kinds of algorithms that does breadth first search and so on. So there is a lot of flexibility to what you can do with all of this. And in fact, this is not just a toy, right? We built a full-fledged industrial strength concurrency library called EIO with this same idea. It has multiple backends, including IO Uring, which is a new asynchronous way to talk to the kernel from the user LAN. It's really wonderful. It sort of makes lots of things much nicer. And EIO is in production in lots of companies. This is based on the very scheduler that I have presented in the earlier slide. And I mean, we are fast, right? So the difference between garbage collected languages and non-garbage collected languages don't matter when you are writing things like web servers, right? Where all of your programs should be doing useful IO. Yeah, it's back. So the graph here is throughput. It shows the throughput. So on the y-axis, you have a throughput offered. On the x-axis, you have the throughput, the requests offered. And you can see that OCaml EIO is faster than Rust Hyper. Don't read too much into these numbers. You can make these graphs light, but it's in the good ballpark, right? You can make things go really fast. This need not be slow. That's the point that I want you to take. Okay, so now stepping back. So we built all of this, and then we want to convince the maintainers to take our idea. So how do you do that? The other thing that we did is we built a wonderful benchmark suite. It's a rigorous, continuous real-world benchmarking suite called Sandmark, where we take multiple compilers. Nightly, we run like thousands of programs, and we produce graphs where you can compare the performance of the multicore compiler and then the vanilla compiler and see what the difference is. And we highlight changes which go beyond a few percentage points so that people are notified and they go and fix the issues. We also built something called OPAM Health Check. The idea here is very nice. So you take your universe of packages, you try to build it with both compilers, the existing one and your new feature. And the existing one is compiler 4 here, new feature is compiler 5. This was many, many months ago. And green here says that the package builds. Yellow here says that the package dependency does not build. And red here says that this package does not build. So because we were very much sort of built on this notion of backwards compatibility, most of these breakages were very small. We were able to proactively go and fix those features, made PRs to the package maintainers. They were able to merge it quickly. We got a good ecosystem coverage as well. The higher level point I want to make is, if you want to contribute to the compiler, you don't have to just work on the compiler code base. There's a lot of infrastructure that really needs your attention, and you can contribute to all of those. This is a very large scale distributed system, right? If you like distributed systems, you'd like building something like this. There are every commit that you make in the compiler triggers some 421 jobs that are parallelly built, right? So you need a very large cluster where you sort of figure out how to schedule this. Very nice problems that are there in compiler development, not just writing the compiler code. Okay, I should finish soon. So I will try to finish soon. So I opened the Multicore OCaml PR in December 2021. It was merged in a month and a half. That's not true. I mean, we've been developing that for like 10 years, right? So the fact that it was merged quickly means that we've done all of the work for a long time. Even after merging, we needed a few more months of iteration to fix the design. It was finally released as a major release of OCaml called OCaml 5.0 in December 2022. And when these large features land, it's never that you're done, right? Oh, features landed, now I'm going to retire. There's always like a asymptotic curve for completion. There's always one nagging bug that is always need to be fixed. So we've been improving it over the minor releases. We still have performance bugs. We know where the bugs are. We just need to push them. There is like lots and lots of work to do here, right? I just want you to, this is not like a closed door. There is always like fun things to do in the compiler land. But there is also some exciting developments in the compiler. So one is called OCaml, which is essentially we are trying to bridge the gap between OCaml and Rust, right? So Rust is great. I like Rust, but OCaml is also great. I like the garbage collector. Most of the times garbage collector is fine. So we are trying to bridge this last mile gap between OCaml and Rust using this idea called modes, which I won't have time to talk to. But we also have much better control of object layout, garbage collection, and so on. This project is led by Jane Street, but it draws lots of lessons from Multicore OCaml. So lots of papers. There is a CI already where you can see whether your package compiles with OCaml or not. But it's different in other ways. So this experimental compiler is in production at Jane Street. So there is a lot of valuable user feedback oriented design, which is very different from how Multicore OCaml was implemented. We did not have users. We had to predict how things go. Here, they can roll out a feature. If it doesn't work, they can roll it back. It's the wild west of compiler development. But if all of this is interesting, you should get involved. There's a bunch of links here. You should have a look and talk to me. I'm going to be around for 2 days, so I'd be happy to talk to you. Thank you.
Thank you for the very exciting talk, Casey.
Thank you.
So we have time for a few questions. Yeah.
Yeah, thanks for the great talk. So I'm a member of the Standard C++ committee and the author of STD execution. So I was curious when you said that I have two questions actually. One is for the parallelization context, right? You mentioned that your slide has a comment that it's not thread safe for C++, but we have been working a large extent to make forward progress ensurement for through XTD execution for all the algorithms that there is, par and par-unsec, whatever it is. So I'm curious as to whether OCaml also takes inspiration from that implementation that we have for execution.
Really good question. Thanks for all of your hard work. I can't imagine working on C++ standards committee because the problems are much larger than what we have in OCaml land. So we did not take, to answer your question, we did not take inspiration. We took probably inspiration from Java, right? Okay. Where any RACI program will have to have semantics, right? It's not just like you sort of limit your programs to have semantics only when you use these things. Use these additional primitives. Any program, even RACI programs, will have proper semantics, right?
Okay.
That's the difference.
Okay. And a follow-up question on that is regarding concurrency. So you mentioned promises and other stuff, right? Futures and promises. So we are introducing reflections in 26, which will probably come up in a couple of. So I think OCaml can also get upgraded with that for the C++ code gen side for.
Yeah, I'd love to talk. I don't know what reflections is, but I'd love to talk about offline. Yeah, okay, so I'm happy to take.
Yeah. These are the questions which I have.
Wonderful.
Another question which I have is just for. Yeah. So.
Offline, I'm happy to take questions.
Give chances to others.
Yeah, sorry.
Yeah.
Yeah, my name is Dibendu. So my question is regarding, what do you see as OCaml's future on the non-CPU side of things, especially GPUs and other accelerators?
So really good question. So we have, the truth be said, we don't have a large ecosystem on the GPU side. We don't have any answers. So we are all binding to C libraries underneath for all of this. But there is an exciting project called Raven, which is trying to build the entire Python ecosystem for the GPU, right? Essentially start from notebooks, PyTorch, low-level bindings, all of these, right? But it's a huge undertaking. There is some momentum behind it, but we do want to get there. But we understand that it's not a language problem; it's a community problem. If people want to hack on GPUs, come talk to me.
Hello.
Thank you.
I'm Mitesh. I work on the JavaScript compiler at IT Bombay. So you mentioned that OCaml compiles to JavaScript. Do you think there is benefit to compile JavaScript to OCaml? And a follow-up question, you talked about implementing effects and the way they are implemented. So when we generate JavaScript code, finalizer blocks look very similar to the way they are implemented in our system. So when we were implementing it, we looked into the scheme's implementation of call CC because that can be used to sort of model all possible these cases. So was the inspiration also drawn from call CC when implementing these FA handlers?
Okay, you had two questions. I'll answer the first one. I don't see how you can easily compile JavaScript to OCaml because OCaml has a stronger type system, right? In a way, we expect things to be statically typed. So I can write very simple JavaScript programs which will not have an equivalent OCaml program. For the second question, yes, it draws from lots of research on continuations, delimited continuations, call CC, all of these. Call CC is undelimited continuation. Here we do delimited continuations. Actually, they are much nicer, well behaved categorically. So the inspiration for us is these operators called shift reset, control prompt. They are like sort of siblings of call CC, right? So we take a huge inspiration from all of that work.
Thank you, Casey, and happy to know that you are around for 2 more days. So,
Yeah, thank you very much
in
for
fact, Casey, to the talk.